we now know how to calculate the proportion of a population and what it means. We can also calculate the proportion of a sample. Now, a sample proportion is calculated just about the same way as a population proportion, but we would do it with our sample data. Now, we want to distinguish our sample proportion from our population proportion, so we use a different symbol. We use P, and then we put this little upside down V looking thing on top of it. It's called the hat symbol, so this is P hat. And to calculate our sample proportion, P hat, we take the number of members of our sample that have the characteristic we're looking for and divide by our sample size. So very similar to how we calculate a population proportion, but we're looking up these values for our sample now. So here, P hat is the symbol we use for our sample proportion. Little x is the number of members of the sample with the characteristic that we're measuring. And n is the sample size. Okay? Now, if we have different samples, we would expect different sample proportions, right? And if in one sample, we might, just by chance, get a lot of members in that sample that have the characteristic we're looking for, okay? But maybe in another sample, just by chance, we don't get very many members from the population that have that characteristic in our sample. So different samples will have different sample proportions. But generally, if our sample is large enough, we would expect the sample proportion to be close to the population proportion most of the time. And the larger the sample is, the closer we expect to get. This is very similar to what we just talked about in the last section when we were talking about how sample means tend to get close to population means. And we formalized that idea with the central limit theorem for sample means. So do we have a similar idea for sample proportions? The answer is yes. We have the central limit theorem for sample proportions. So let's write this down because this again is a very important theorem. Central limit theorem for sample proportions. So we're going to consider a population. And let P be the proportion of the population that possesses some characteristic. Okay, so just the population proportion for something that we're measuring. Be the proportion of the population that possesses some characteristic, okay? We are going to let P hat, big P hat, be the random variable of the sampling distribution of sample proportions. Random variable of the sampling distribution of sample proportions. So in other words, if we could look at all the possible samples that we could take from this population of a certain size, okay? And I should probably add that where the samples are of size n. So if we could take every possible sample of size n, whatever n is, and look at their different sample proportions, we would get a sampling distribution of those sample proportions. Okay, we would be able to compare where they fall. Now, most of those sample proportions, as we've already discussed, we expect to be close to the population proportion. But just by chance, some sample proportions, a few, may be pretty far away from that population proportion, right? If the sample size n is big enough, and in this case, big enough means so that, let me scroll down just a little bit, so that n times p is at least 5, and also n times 1 minus p is at least 5. Okay? Then the sampling distribution is roughly normally distributed with mean the same as the population proportion and standard deviation equal to square root of p times 1 minus p divided by n. That is, as long as n is large enough, that sampling distribution of all possible sample proportions is normally distributed, and the mean of that distribution is the same as the population proportion, and the standard deviation of the distribution is p times 1 minus p over n. Okay? So this is very similar to our central limit theorem for sample means. Okay? In both cases, if we looked at the sample statistic that we are interested in and looked at all possible samples and the statistic that we get, it tends to be close to the population parameter we're estimating. Okay? And then we have a measure of how far we might deviate from that population parameter, our standard deviation. Generally, a larger sample size means your standard deviation will be smaller. Remember, larger denominator means smaller fraction. So as our n gets bigger, as our sample size gets bigger, that means our denominator of this fraction is getting bigger. So the standard deviation is getting smaller. That means that for larger sample sizes, our sample proportions tend to get closer to the population proportion. It tends to better approximate that population proportion. Okay? A couple of other points. As with our central limit theorem for means, we need the sample size to be big enough in order for this to work, right? And then we are roughly normally distributed. As long as your sample satisfies this, as long as it's big enough so that this condition is satisfied, then it's so close to a normal distribution that you could just consider it a normal distribution. Okay? You don't have to worry about the roughly part. Also, just like for the central limit theorem for means, to avoid confusion, we call the standard deviation of a sampling distribution, we call this the standard error. Okay? So we don't call this the standard deviation, even though it is one. To avoid confusion, we call this guy the standard error. Okay? Now, with this in mind, let's talk about calculating z-scores and how this would work, right? We're dealing with a normal distribution, and so we want to calculate be able to calculate z-scores so that we could calculate probabilities. The relationship between a z-score and a particular value is still the same as it's always been, but again, we're using different symbols here. So our general formula for a z-score, remember, is z equals the particular value minus the mean over the standard deviation. Or if we're interested in finding x, we rearrange it so that the x is by itself. Same formula, we just get the x by itself. And we get x equals mu plus z times sigma. Okay? That's the general formula to relate the particular value to a z-score. Okay? But for our particular problem, for this sampling distribution, we are using special symbols for the mean, special symbols for the standard deviation. Okay, so let's swap out the symbols here so that we know what this is going to look like for this central limit theorem. So when we're dealing with the central limit theorem for sample proportions, these same formulas take on a different look. This first formula, we still use z to represent the z-score, but our particular value now would be a sample proportion. Okay, so instead of x, we use p hat. The mean of the distribution is p, the population proportion. And then the standard deviation of the distribution is right here. We call it the standard error. And so that's what goes in the denominator here. P times 1 minus p over n. Okay, and if I rearrange it so we get it to be in this form, we get our particular value p hat equals the mean, which is our population proportion, plus the z-score times our standard error. P times 1 minus p over n. And so these are the formulas that relate our z-score in a standard normal distribution to a particular sample proportion value p hat in our sampling distribution.